So greetings to everyone. So let us continue the previous topic, that is welded plate girder design along with intermediate stiffener. So far we have discussed some 6 steps. In that, right now we are in end bearing stiffener design. Okay, so we have chosen that 190 mm by 20 mm, two flats to be used as a end bearing stiffeners. So whether this can satisfy our requirements or not, that we are checking. Okay, now so this dispersion length, maybe it is 2 times of thickness of web, 20 times of thickness of web. Okay, on each side. Okay, so in that, the first check is check for buckling stiffener. Okay, that check for outstand of stiffener. Okay, now so that is within the limit, that is between 14 times of TQ into epsilon to 20 times of TQ into epsilon. Okay, so actually we have provided less than, that is less than the requirement. Since I said if it is flat with respect to its dimension, if we are going to give, it is 295 mm. So if we are going to provide around 280 mm, it will occupy completely. So it is not an economical section. That's why we chosen 190 mm. Okay. So for that we have done one check, which is nothing but check for buckling of stiffener. Okay. So in the buckling, it is safe. Okay, that is P should be greater than, P should be less than PD, design compressive strength of the member. So it is safe to carry the buckling force. Okay, now let us move on to the load carrying capacity. Okay, so this load carrying capacity is nothing but like a local capacity of web. Okay, local capacity of web, so which is nothing but from class 8.7.4, page number 67 of IS 800 2007. So the formula F1 is equal to FW is equal to B1 plus N2 into TW into Fy by gamma m naught. Okay, so we have to assume, so this is our plate girder. So this plate girder is going to place over the bearing pad. So that bearing pad I am going to assume as 100 mm. So which is nothing but B1. So B1 I am assuming as 100 mm. N2. So this is nothing but our dispersion. Okay. So here I am using 50 mm as our flange plate thickness. Okay. From here it is going to expand it. Okay, now so this inclination is nothing but n2, that is 2.1 is to 2.5 is the ratio. So here if I'm going to give this, so I'm having the 50 mm height of flange. Okay, so if I'm going to have a dispersion with respect to this thickness, that is 1 is to 2.5. Okay, which is nothing but 50 into 2.5. This is only one side. Okay, so B1, this is 100 mm is the B1 value. With respect to flange, the dispersion is going to be like this, 50 into 2.5. So N2 is only one side, 50 into 2.5. So which is nothing but 125 mm. So therefore I am going to check it whether I have to provide the stiffener or not first. So FW is equal to B1 100 in plus 125 into thickness of web is 10 mm and Fi is 250 divided by 1.10. So if I'm going to substitute these values, I'm getting the value of around 511. Okay, so Fw is the value of 511.36 kilonewton, which is greater than our actual shear force created in the plate girder, that is 1908 kilonewton. So this is greater than the value. So we are in need of stiffeners. Okay. So for how much value I have to resist with the help of stiffness? This is nothing but bearing stiffener. Bearing stiffener will be designed for the value of, so that is the balance force. Okay, that is nothing but V minus Fw. For this value I have to design kilonewton minus 511.36 kilonewton. So if I'm going to give like this, it becomes 1396.64 kilonewton. So for this value I have to do the design of bearing stiffness. Okay, now I am going to check whether my stiffness whatever I have chosen is safe to transmit this force or not. That I am going to check it. Okay, so first the bearing capacity of the stiffener alone. So our stiffness is 190 by 20 mm. Okay, so I'm going to use the formula. Bearing capacity of stiffener is equal to area of the stiffener multiplied with stress, that is Fy divided by gamma m naught. Okay, so area of the stiffener I have to calculate. Okay, so we all know that so here I have the coping of 15 mm. Then after I can have our stiffener, sorry, stiffener plate. Okay, so I have to deduct this coping from the stiffener length. That is 190 mm I am going to provide. So in the width I have to deduct this coping. So 2, 1 and 2. There are two stiffener end bearing stiffeners. Okay, so 2 into 190 minus 15 into 20 mm. Okay, so which is nothing but 2 into 190 minus. So 7000 mm squared is the area of stiffness. Okay, so Fi value we know that 250 Newton per mm squared, and the gamma m naught we know that. Therefore, bearing capacity of stiffener. Bearing capacity of stiffness. So area 7000 multiplied with the Fi value 250 Newton per mm squared and divided by gamma m naught. So safety 7000 into 250 divided by 1. It becomes 1000 990.90, 1590.91 kilonewton. So this is the my bearing capacity of stiffener. Okay, but actually I need to design the stiffener to withstand this much force alone. Okay, that is 1396. But actually the size I have provided 190 by 20 mm. This okay, now this bearing stiffener I have provided already. So this will resist, yeah, shear the force of 1591 kilonewton. So which is greater than our actually created 1396. Okay, so which is safe. That is the end bearing stiffener 2 into 190 mm by 20 mm flat. Okay, is safe to transfer the bearing forces. Okay, so hence it is safe. So this is the way we have done the check. Okay, so the end bearing stiffener, whatever we have chosen, that will be safe in all the aspects. Okay, that is what that 190 mm by 20 mm by 2000 mm height. Okay, will transfer the forces effectively to the support. This is with respect to the end bearing stiffener. Now let us move on to the intermediate stiffener. So with respect to our section size, 2000 mm, 10 mm, 600 mm, 550 mm. Okay, so with respect to this, so we have designed the end bearing. Okay, so the end bearing stiffener of size 190 mm by 20 mm by 2000 mm, which is safe to transfer the all forces. This is 20 mm and the height is 2000 mm. So this is safe. Now we have to design the intermediate stiffeners. Okay, so it's with the thickness we have to assign, and we have to check it whether it is safe to transfer these forces, the bearing or whatever it may be, the load carrying these things. Okay, so let us move on to the design of step 7. Design of intermediate stiffener. Intermediate stiffener. Okay, so uh, we had one formula which is, so just I will share the code book so that it will be easy to use. So in the code book, so in the code book page number 66, page number 66. Here we can have some requirement. Minimum stiffness. This is with respect to our intermediate stiffness. Okay, whether it is satisfying the minimum requirement or not. First, we should check it whether the C by D distance should be greater than or equal to root 2. So that we have to check it. So C value, we know that 2266, sorry, 2666.67 divided by D value is 2000. Okay, this value comes around 1.33. So root 2 is nothing but 1.414. So definitely it is more than root 2. Okay, C by D value is more than root 2. So if it is more than root 2, then what is the things? Sorry, it is 1.33, which is less than root 2. Okay, so if it is less than root 2, what is the stiffener moment of inertia we have to provide? We have one formula. Okay, so from that formula we have to check it whether whatever the section we are going to choose, whether it is withstanding or which is greater than this is. Okay, so that we have to check it first. So let us do that. Okay, so here from page number 66 of IS, sorry, class 8.7.2.4 of IS 800 2007. Okay, C by D value we have to collect it. So there are two categories. One is C by D is greater than root 2. Second class is C by 2, which is less than or equal to root 2. So this is our constraint. Okay, sorry, less than root 2, greater than or equal to. Okay, so C by D. So here our spacing between the two stiffener is 2666.67 divided by our depth of web is 2000. So it becomes 1.333. So root 2 value, if I'm going to give, I'm getting 1.414. So this is less than root 2. Then we have to go with the second condition. So C by D value is less than root 2. Therefore, our IS value is greater than or equal to 1.5 into D cube into TW cube divided by C square. So I have to calculate this value. So 1.5 into D is nothing but depth of web, which is 2000 mm, and the thickness of web is 10 mm divided by C square. It is spacing between the stiffeners. If I am going to substitute this, I can get I'm getting around 1.687. 1.687 into 10 to the power 6 mm power 4. Sorry. So I have to choose one section, that is one flat. So as usual, if I'm going to, this is my top view. If this is my web plate of 10 mm thickness, okay. So by either side, I'm going to provide the flats. Okay, so this flat size I have to assume this is nothing but our intermediate stiffness. So I have to assume the stiffener size, flat size. So from that I have to check the I value, Ix value. If it is greater than this Is, then it is safe enough to transfer the or carry the force. Okay, so let us try with the section. So we are going to assume, so assume two numbers of 110 mm by 12 mm flats to be used as an intermediate stiffness. Okay, so first I have to check Ixx value. So Ix value is nothing but BD cube by 12. So plus A y bar square. So in this diagram, this is 110 mm and this is 12 mm. Okay, so I can have two numbers. So B into D cube divided by 12 plus A y bar square. So 12 into 110 into y bar square. So for one section it is 55 mm. So 55 square. So 12 into 110 cube. Yes, 12 into 10 into 55. So it is comes around 1.69 into 10 to the power 6 mm power 4. So this is Ixx provided. So I have to check with the requirement. So my requirement is 1.687, but actually I have provided 1.694. So which is greater than my requirement. Hence it is safe to with respect to the moment of inertia. Hence safe with respect to moment of inertia. Then next I have to check it in the two things. One is with respect to the outstanding of stiffener. Then another one is with respect to buckling. Okay. So check this step 7.1. Step 7.1. That is check for outstanding of stiffener. So it is nothing but we all know that so BS provided is equal to 110 mm. Our requirement is 14 times of TQ into epsilon to 20 times of TQ into epsilon. Here TQ is equal to 12 mm. So how much it will be? So 14 into 12 into 1. So our epsilon value is 1. We know that it is root under 250 by Fy value. So it becomes 1. Okay. So if I am going to put this 14 into TQ into epsilon, then it will come as a 168 mm. And if I am going to put 20, then it becomes 240 mm. Actually, I have provided only 110 mm. So because of economical consideration, so I have to check it. Okay, whether it is safe enough to carry the buckling forces or not. If it is carrying the buckling forces, then it is safe. Okay, so check for buckling of stiffeners. Okay, so here buckling force FQ is equal to V minus VCR divided by gamma m naught. Okay, so what is V and what is VCR? Okay, so total load. So while discussing the problem, we have done the total, that is load calculation. So in the total load acting, it is factored load, total factored load acting on the girder is becomes 159 kilonewton per meter. Okay, so therefore shear force for this section. So force into distance. Okay, here distance is nothing but spacing. It is how the weight is going to distribute it. So 24,000 minus 67 divided by 2. So 159 into 100 minus 2666.67 divided by 2. It becomes 1695.99. So now it is nothing but 1696 kilonewton. This is V. 1696 kilonewton is the V. And VCR is nothing but with respect to FW, how much load is going to withstand. That is called our VCR. So that value is around 689.86.9. Okay, therefore remaining forces FQ is equal to 1696 minus 686.91 divided by 1.10. So it becomes the value becomes 917.36 kilonewton. So our section has to transfer this force, okay, which means now I am going to calculate the design strength. So if the design strength is more than this value, means it is safe to transfer the force. Otherwise, I have to redesign the section. Okay, so let us move on to the sectional design strength of the stiffener. Okay, our stiffener size is 110 mm by 12 mm. Okay, so we have to calculate the Ix value. So BD cube by 12 plus AY bar squared. So B is nothing but 12 into 110 cube divided by 12 plus area 12 into 10 into 55 squared. So it becomes 532.4, or else 5 into 10 to the power 4 mm power 4. This is Ix value. Okay, so why I have to calculate now? The design strength of the stiffener is equal to AE into FCD. Okay, so AE is equal to, we already said that two numbers are there. plus 2 into 20 times of thickness into Feb. So 5320 mm square area. Okay, next we should move on to the FCD value. If I need FCD value, I need KL by R minimum value. So if I need R minimum, it should nothing but Ix by A. So I value is 532.4 into 10 to the power 4 divided by area is 5320. So root under becomes 31.63. Okay, therefore KL by R minimum value, comma, Fy is equal to 250 Newton per mm square, and buckling class for welded girder is C. So from this table 9C of IS 800 2007, we are going to calculate the value of FCD. So that FCD is nothing but KL by R minimum value we have to calculate. KL by R minimum. So 0.7 into 2000 by R minimum is equal to 31.63. So it becomes 44.26. Okay, therefore from the table 9C. So I'm telling now that buckling classes that should be from here. Okay, so the welded I section, the buckling class is about C. Okay, that's right. Then from table 9C, KL by R minimum is 44 and 250. It is around between 198 to 183. Okay, so we are going to take approximately 192. So we have to do some process. After doing that, we are getting FCD values 192 Newton per mm square. So if I'm going to substitute this, then design bearing strength becomes intermediate stiffener becomes AE 5320 multiplied with FCD value 192, around 1021.4 kilonewton it can transfer. Okay, but actually we are getting around 917.36 kilonewton because of load. So it is lesser than our design strength. So definitely it can withstand. Hence the stiffener is safe in bearing transfer. Okay. Thank you.